from DFKI.
Yeah, so I'm presenting today the work also mainly from students from the University of Kaiserslautern today. We are focusing mainly on deep learning. So first of all, like you already saw it in the images, they look quite similar. So how well do these deep features basically work on this? And second problem is, can we use pre-trained models which you already see for autonomous driving? How easily can we apply them also for semantic segmentation on remote sensing? So first of all, we trained the provided features here using SVM as a baseline classifier, using a 80-20 split, and you actually see that it's just 15% better than the statistical baseline. So therefore, we extracted feature from different models here, all trained on ImageNet, and you see they're actually performing better than the traditional approaches by about 20%. What we also did is we tried Deep Sentibank. This is a specific model which focuses on extraction of adjective noun pairs. So it's trained on the visual sentiment ontology, and the difference between ImageNet and this Deep Sentibank model is basically to not just predict objectives, but to predict, for example, a cloudy sky, red roads, damaged house. So you have a more descriptive information of the image. And the second thing is you have a less domain change, because the VSO is also basically trained on the ViVeCC or a subset of the ViVeCC. So the images are quite more scenic compared to the ImageNet dataset, which is very focused on objects. So that's why this is better. And here you see we basically used REF SVM using the XResNet. That's a ResNet using cross-residual connections to predict multiple tasks. And we basically use this feature for the retrieval task. And here you see on our development set some experiments. So it's getting very high accuracies. You will also later see the results on the test set. For the metadata, we did also some evaluation on different types like titles, description, and user tags. We figured out that user tags are less ambiguous and most reliable. So therefore we trained a word embedding on this using Word2Vec, and we basically represent each social media report or document as a mean of these word embeddings. And something that we also figured out gives a big improvement by about 10 to 15% is an additional weighting of TF-IDF for the word embedding when computing the mean of these vectors. And we always apply the same approach using SVM, training this and taking the confidence or the distance to the decision boundary as a ranking for our approach. And for the multimodal fusion, we just concatenate the different features and apply the same approach. And here you see the different results. The first outcome is that here the visual and metadata features perform best in combinations. Also, you see here the comparison ImageNet compared to this Deep Sentibank model is also a significant difference by about 10% points here. So these are the results for the first task. And for the second task, we first of all had the challenge to really train the networks from scratch. So we applied a lot of data augmentation on it. For example, here different random flipping and also rotations in order to extend the data set. And something that we also faced is that quite often you cannot use the 16-bit images from satellites with the normal framework. So we also encoded this into 8-bit pixel representation, and we tried 3 different approaches. One is using a standard convolutional neural network, which is used for semantic segmentation quite often. However, the problem is that these models just take the RGB channels. So therefore, we did in the first experiment also just use the 3 channels from the satellite. In the second approach, we additionally extended the first input layer to also cope with the infrared information. And you will later see that this is of great importance for the flood detection. And finally, we also investigated into a more sophisticated decoder by not just upsampling the final feature map, but also attaching a reverse encoder basically to the model. And here are the results which you see. So one major outcome here is that infrared is important to incorporate this into the models because it gives some information about soil moisture, about water basically, and also the more parameters basically in the encoder help the network to learn a bit better predictions basically, or better segmentation masks. Our main conclusion of this approach, first of all, multimodal fusion also turns out for us was achieve the best results. Not all image net pre-trains are best to apply, so sometimes it makes sense to look at different domains and how they were trained on which data set. TF-IDF weighting on word embeddings also gave us big improvements for this metadata retrieval task. And finally, also infrared information is quite important for our segmentation network. That's it.